This lecture is on silicon wafer circuit fabrication, and we're going to look at some basics of doping silicon, and then talk about how wafers are made, and then how the integrated circuits are created onto the wafers. Now, the most common semiconductor that's used in electronics is silicon, and semiconductors are materials that are mediocre electrical conductors, so they're not as good as conductors like copper, silver, and gold, but they're not as bad of conductors like insulators are, like paper or Teflon or mica, material like that. Now, to increase the conductivity of semiconductors, there's this process known as doping, which is adding another substance to the semiconductor called an impurity, where either that impurity has one more valence electron than what the semiconductor has, so in this case one more valence electron than what silicon has, or adding an impurity, a material that has one less valence electron than what the semiconductor has. So when you add a substance that has one more valence electron than what the silicon has, that's called N-type silicon. And when you add a substance that has one less valence electron than the silicon, that's called P-type. And a common substance that's used to make N-type silicon is you add phosphide, and for P-type you add boron. Now, phosphide to make the N-type is called a donor atom, and I'll explain why that's so. And then when you make P-type, a material like boron is called the acceptor. And I've got a couple of diagrams coming up where I'll explain why in this case it's called a donor, and in this case it's called an acceptor. Now, these doped semiconductors, okay, so like the doped silicon, they're used to make the fundamental component of an integrated circuit, which is a device called a transistor. So here's a diagram of an N-doped silicon, and looking at this diagram where you see the +4 with the 4 dots around it, this represents a silicon atom. Silicon has 4 valence electrons. Okay, the valence electrons are the electrons on the outermost orbit of the atom, and those are the electrons that can contribute to a current. And what determines the conductivity of a substance is how many charges, whether they be electrons or positive charges, that are unbounded, that are not part of a bond to another atom. These bonds between valence electrons between the silicon atoms, they're called covalent bonds, which just means they have average strength. In conductive material like metals, these bonds between valence electrons are very weak, and that's why metals have very high electrical conductivity. And then materials that are insulators, these bonds are very strong, so that's why insulators like Teflon and paper and things like that don't conduct electricity very well, because the bonding between their valence electrons is very strong, so you don't have as high as conductivity as, say, with the metals. Well, semiconductors like silicon, the bonds between the valence electrons are average. I mean, that's what covalent means, is just they have mediocre strength, and that's why they're in between conductors and insulators as far as their electrical conductivity. So in this diagram, all these are silicon atoms here around the perimeter, and then to make an N-doped silicon, you would add a substance that has one more valence electron than what the silicon atoms have. So for example, a phosphide atom has 5 valence electrons. So for the 5 valence electrons of the phosphide atom, they match up, make bonds with surrounding valence electrons of nearby silicon atoms. But that 5th valence electron doesn't have another valence electron to pair up with. So that becomes what we say unbounded or free, and therefore it can contribute to a current, and that's what increases the conductivity, is the fact that now there's this free electron. And of course, the more phosphide atoms you add, the more free electrons you have, and the higher the conductivity of the n-doped silicon. And this phosphide atom is called a donor atom because it's donating, if you will, its free electron to increasing the conductivity of the silicon. Okay, p-doped silicon, it's just now the substance that's added, often in the case of silicon, boron. Well, it has one less valence electron than the silicon atoms have. So what happens is a nearby silicon valence electron will actually drop down into the orbit of this boron valence orbit. And the reason for that is because the boron valence electrons are at a lower energy level than what the silicon valence electrons are. So that's why you have this dropping down to the lower energy level. And that's where the name acceptor comes from. Okay, since this valence electron of the nearby silicon atom is being accepted, if you will, by the boron atom. And when this valence electron drops down in energy level to the boron valence orbit, well, it leaves a space here which acts like a positive charge, and that's where the p-doped name comes from. The fact that now you have free positive charge that can contribute to a current, and it has the same effect of a free electron, where the free positive charge increases the conductivity of that doped material. So at this point, I would like you to watch this video. You know, after my presentation here, watch this video, and this video goes over the basics of a transistor switch. And you don't have to watch the whole video. This is part of a larger, about a 1 hour video. Actually, I think it's more like 40-minute video called Silicon Run. This video in parts is available on YouTube. So for this particular topic, transistor switch, if you watch the video from approximately the 3.5 minute mark to the 5.5 minute mark, it covers the basics of transistor switches. So after this presentation, you know, watch this video. I'll have a video worksheet for you to fill out as you watch this video, as well as there'll be several more videos that I'll also have you watch that has to do with this discussion. Okay, well, the first step in producing a silicon wafer is to refine raw silicon. And raw silicon is obtained from beach sand. The sand is heated with gases up to a high temperature, 1700 degrees Celsius, and this is to separate impurities. Now, silicon is very abundant. In fact, it's dirt cheap because it's so abundant. It's found in the Earth's crust. You know, the chemical makeup of the Earth's crust is approximately 28% silicon. So silicon comes from beach sand. And refined silicon is called polysilicon. And this is what it looks like over here. It kind of looks like charcoal, but it has a lighter color to it. Now, these are the processes involved with silicon wafer fabrication. We are going to look at crystal growth and the slice and polish, and then also the cyclical, these cyclical processes here during today's class. The rest of this, the testing, the sawing and breaking, and in assembly, IC assembly, that will be talked about in the next lecture. Okay, so the polysilicon, those chunks that kind of look like charcoal, which are the refined silicon, they can't be used directly to fabricate the wafers, but they have to be further processed, and they're converted into a monocrystalline structure that contains a single crystal, um, or it becomes a single crystal with uniform structure. So the silicon nuggets, those polysilicon chunks, they're placed in a crucible and heated to a very high temperature, like 1400 degree Celsius, something like that, which is the melting point of silicon. And then from that molten silicon, a single crystal ingot is grown, and it's grown from a seed, which is a small piece of silicon crystal. And there's a video that I'll have you watch that shows this taking place. That's actually kind of cool. And then once that ingot is formed, the ingot is sliced into the wafers where the integrated circuits are then created on. And if you grow an N-type crystal structure, well, a small amount of phosphide dopants would be introduced to this melting. And if you want to grow a P-type crystal structure, well, a small amount of boron would be added to this melt. Now I have, here in my office, I have one of these ingots. Okay, it's right here. Okay, so this is what it looks like after it comes out of that crucible and it's had time to solidify. This ingot here is about a foot long, and it's really heavy. It probably weighs a good 30 or 40 pounds. Okay, so this is the ingot, and you'll see in a video later on that this ingot is then sliced into wafers, and then the integrated circuits are placed on that wafer. In fact, here, see, here's a wafer that has the integrated circuits fabricated on it. See, all those little rectangles are individual integrated circuits. At the very end of the process, each of those little rectangles, they're called dies, are cut out, and then they become an individual IC. So, this is like the starting point, this ingot, and then this is close to the final product. It's just that we probably have a few hundred integrated circuits on this one wafer that eventually get cut. Okay, get cut out. Okay, so as I mentioned, the wafers are cut from that ingot, and then they're go through further processing where they're polished and cleaned up, and you'll see this process in a video. In fact, this video here, if you started at approximately the 3:30 time mark and run it to the end of the clip, and then this next video, if you watch this from the start till about the minute 45 mark, it will go over that wafer prep that we just talked about. Okay, so we've gone over crystal growth, the slice and polish. Now we reach this cyclical processing here, which involves depositing or growing a film, and then some photolithography. So you'll see that this is the same concept as what was used in PCB fabrication to get the image of a circuit onto a printed circuit board. It's the same idea, okay, the same concept that's used here to get the integrated circuit onto the wafer, okay, involving photoresist and a mask and UV light for exposure. It's just here the dimensions are a lot smaller. Okay, then etching. Okay, so Also, again, similar, at least conceptually. The actual mechanics of it is a lot different because, as you'll see, chemical acid isn't used for the etching, but something called a plasma etcher is actually used. And then ion implantation and diffusion. Okay, and these processes are repeated as many times as needed. You'll see that integrated circuits are built layer by layer. And as I said earlier, these other processes after these cyclical processes, this will be talked in the next lecture, IC assembly. Alright, so these are the 4 major IC fabrication process steps. And as I mentioned before, they're repeated as many times as necessary to build the IC layer by layer. So you have deposit or grow film, so either insulating or conducting or conductive material is deposited onto the wafer. Silicon nitride is a insulator. Also, there's growth of thin layers of silicon dioxide, which is also an insulator. Conductive materials that are used in IC fabrication are doped polysilicon, along with tungsten and aluminum. Then there's the photolithography stage. Okay, and this is transferring the circuit patterns using mask and photoresist and UV, like I mentioned just a while ago, to get the circuit patterns onto the wafer. And again, same concept as PCB fabrication, except at smaller dimensions. Okay, then there's an etching stage, which is used to do several things, removing silicon dioxide to form stencils, and also removal of these other materials, okay, listed up here. Conductive materials like dope, polysilicon, tungsten, and aluminum. And then there's a stage, the ion implantation and diffusion, and this is to create the N or P regions which make up the transistor. Alright, so oxidation, which is referred to as growing the oxide. Silicon dioxide is a very good insulator, and this oxidation process is forming silicon dioxide on the surfaces of a silicon wafer. And this is done by heating the wafer in an atmosphere of pure oxygen at high temperature between like 900 and 1200 degrees Celsius. And this process of growing the oxide, it's used in different points of the fabrication sequence for various reasons. Sometimes the silicon dioxide is used as a stencil, sometimes it's used as a barrier, and other times it's used just as an insulator, which that's what silicon dioxide basically is an insulator, but it's used in a couple of different ways as an insulator. One way is to insulate between devices, insulate between the transistors that are on the wafer. And then also, as I mentioned earlier, how ICs are built layer by layer, well, the layers are insulated with the silicon dioxide. So the silicon dioxide provides many uses. Okay, so the photolithography part of the process, like I said earlier, is much like what we talked about with PC fabrication. That just like photoresist is put on the copper of a PCB board, okay, to do the imaging of the circuit onto the PCB board, well, photoresist is put on the surface of the wafer so that we can transfer the image of the integrated circuit onto the wafer. Now, one difference between the PCB and IC fabrications in this regard is that with PCB fabrication, the photoresist is most often negative photoresist that hardens when it's exposed to UV light. With the ICs, positive photoresist is typically used. And positive photoresist, it becomes softer when it's exposed to UV light. Okay, so you have positive photoresist that's placed on top of the silicon wafer, and then the image. Now, you know, in PCB fabrication, the mask, okay, is often called a photo tool. With IC fabrication, it's called a reticle. Okay, but these terms all mean the same thing: reticle, mask, photo tool. It's the negative of whatever circuit that you want to image onto the photoresist. Okay, so you shine UV light through the reticle, the mask, and just the areas that correspond to the transparent parts of the mask will be exposed. Okay, the photoresist that corresponds to the transparent areas of the mask, that's the photoresist that gets exposed and will become softer than the photoresist that is not exposed. Alright, so this is looking at the photolithography in a little more detail here, along with the etching that takes place after the exposure. So you start off, the silicon dioxide is grown on the wafer, okay, on the surface of the wafer, and then the positive photoresist is applied. Okay, you put the reticle between the UV source and the photoresist. Okay, and then you shine the UV light, which is going to expose the photoresist that's underneath the transparent areas of the reticle. So this is the photoresist here, shown in purple. That's going to become softer than the photoresist in dark blue, okay, because the photoresist in dark blue being underneath the dark areas of the mask, okay, dark areas of the reticle are not exposed to the UV light. Okay, then the developer will remove the exposed photoresist, and then the etchant is going to take away, the etchant will take away the silicon dioxide, and then the last part, the stripping, the cleaning type solution, will remove the unexposed photoresist. So what you're left with at the end is you're left with the wafer with just these areas of the silicon dioxide, and here you'll see that the silicon dioxide is going to act like a barrier when we go to dope the wafer with the ions, either make p-dope or n-doped. Okay, just a comment on the etching, and I kind of gave a little preview of this a while back, and that's unlike with printed circuit boards where the etching is typically done with a chemical. With ICs, the etching is done with what's called a plasma etcher, and the reason for that is because plasma will only etch in one direction, where chemicals etch in all directions. So what happens when you use chemicals to do the etching on an integrated circuit is that you won't get nice vertical walls. Because the chemicals etch in all directions, you'll get this sloping that's shown in this picture here. Okay, and it leads to what's called undercutting, and that can actually detriment the performance of the integrated circuit. So the plasma etching, which uses fluorine atoms, gives much steeper cuts. Like, you won't get this slopiness like you do with the chemicals. So it's much improved. The etching is much improved by using this plasma etching. And in the video, one of the videos that you'll watch at the end of this presentation, they'll show you images. Okay, images taken with high-powered microscopes that show how how you don't get the undercutting with the plasma etcher. Okay, so this stage here, the ion implantation and diffusion, well, this is where, or this is how the N-type or P-type regions that will end up being what are called the channels, transistor channels, are developed. Also, the same process would be used to make the regions of the transistor that are called the drain and the source. So you can see these little gold balls, those represent the impurities. So this could either be P-type or N-type ions. and the blue is the silicon dioxide, and the green here is the wafer. So you'll see that these ions, when they hit the surface here of the wafer and the silicon dioxide, well, the ions that hit the silicon wafer directly will be embedded in the silicon, and then the wafer is heated up to diffuse those ions into a larger area of the wafer. But the ions that hit the silicon dioxide, the blue here, will be absorbed and therefore won't make it and won't penetrate the silicon wafer. So you see, it's just the ions that hit the green wafer. Oops, it kind of ended quick there, but in the video it shows where the ions hit the green wafer getting a darker green because they actually penetrate into the wafer, but those ions hitting the silicon dioxide are absorbed and never make it and never penetrate into the wafer. So it's the silicon dioxide that's being used as a stencil, as you will, to determine what areas of the wafer get doped and which areas do not. Okay, so after the ions are penetrated into the wafer, heat is used to diffuse those ions deeper into the wafer, and it creates what's called a well. And this well will end up being the channel of the transistor. And then later on each side of this well, this channel, the same sort of process will be used with a different mask, okay, therefore creating a different stencil, where we'll dope the areas around the well the opposite type. So if this well was a p-type, okay, if we used a p-type dopant for this well here, well, we would have n regions around, okay, and those regions around this well, this channel, are called the drain and the source. And that's what makes up a transistor, are these three regions, the channel along with the drain and the source, that are on each side of the channel. So if the channel is p-type, your drain and source are going to be n-type. If your channel is n-type, your drain and your source are going to be p-type regions. Okay, so IC fabrication, as I said earlier, is done by building a layer at a time. Each layer is patterned using photolithography. You'll see that typically there's a dozen or so, a dozen or even more. Usually a dozen is the smallest number of masks or reticles that are used to build an IC. Okay, because each layer needs that photolithography stage to image the circuitry or the pattern for the particular layer that you're making. Okay, I already mentioned about this the previous slide, that the highly doped regions on each end of the well, that's the drain and the source of the transistor. The gates of the transistor are made with doped polysilicon. You have various layers of silicon dioxide that provide electrical isolation, okay, either between the transistors or between the layers. Conductive material that's used, tungsten and aluminum. Tungsten is used to connect these highly doped regions, which are the drain and the source, to the aluminum, and the aluminum is what provides the connection between the drains and the sources of the transistors on the wafer. You'll have millions, if not billions, of transistors on a wafer, depending on what particular device it is. And then silicon nitrate is an insulated material that is put on top of the aluminum, and also to keep the silicon dioxide from growing after the circuitry, the IC has been made. So here's a picture of a single transistor. Okay, see right here, the well, which you can see is right underneath where the gate electrode is, which again is made of polysilicon, doped polysilicon, and then you have highly doped regions on each side of that well. Also, the well you can call a channel or substrate. Okay, so there's various names for this well. You'll see in the video it's called a substrate, a It's also called a well, I think, in the video at some points. And then really what it ends up being, at least from the device perspective, is the channel of the transistor. Okay, so well, substrate, channel all mean the same thing in this case. And that corresponds to the gate. Okay, the channel corresponds to the gate, and then you have the drain and the source on each side of this channel. And then the tungsten plugs is what connects the drain and source up to the aluminum, and the aluminum acts like the copper on a printed circuit board. Okay, it just connects all the drains and sources on the transistor. You know, this is a single transistor, but on a typical IC, again, you're going to have like hundreds, thousands, even, you know, millions. You know, like microprocessor ICs have millions, if not billions, of these transistors. Okay, and they're all interconnected by this aluminum. The silicon dioxide, you know, provides isolation between transistors, also between, you can see here, the gate and the plugs that connect to the drain and the source. And then a silicon nitride is an insulator that's put over the top, okay, over the top layer, that protects the aluminum and also keeps the silicon dioxide from growing any more than what we want it to be. Okay, so the last part of this discussion is just to watch this this video, and you would want to start this video at the 1440 mark. So all these videos, I think this is the fourth one that I've that is part of this presentation. All these videos came from the same source, which is a Silicon Run video off of YouTube. Like I said, this video on YouTube is in segments. Okay, so watch the videos during the time marks that I mentioned. I also put the time marks on Canvas, and there is a worksheet. Okay, this worksheet here that's on Canvas. Okay, so IC Fabrication worksheet. It has 20 questions. So as you're watching the videos, complete this worksheet and then upload it to Canvas, because this is a graded assignment. Okay, so that finishes IC Fabrication, and then we have one more manufacturing lecture on IC assembly. So I will see you then.